Now, today's topic is we are going to prove something about boundary of Cartesian product of two space. It's like you have assume that you have x and y, and their product is x Cartesian product with y. So we are wondering what is to be like their boundary. How can we measure it? How can we calculate it? So before that, we have a lemma, a little lemma. So you have x and y, and you have a picture of it like x is here, from this to this, x, from that to there, you have y. So you you take complement of in the spaces. Okay, let's a subspace or subset of x, and b is subset of y. So it's like there are some subspaces, but to work with some convenient way, we are taking like a is from there to there and b is from there to there, right? So what happens if you take out of a Cartesian product b from x and y? So your answer isn't, this answer isn't correct, which is an x minus y minus b, because that means that you have an x and y here, the whole square, but you take a complement here and you end up with this little square, well, which is not correct, right? Because you are lack of this part and this part. So you need to think that, and it's lemma, but it's sketch of proof. The proof is that in the result of this is something called, so you are excluding this part, right? And you need to include these three parts. So you unite these parts with this. So how do you write this little square, not square but rectangular box? So it is x minus a, right? You write the first Cartesian product with the whole y, and you end up with this part, right? This rectangular box, but you are still lacking of this little part. So you unite with similar way. You in the second part you unite with y minus b with the whole x. So it's like Leibniz product in differential. Okay, so you unite with this part, this little square rectangular box with this rectangular box. Okay, you have additional part, you are summing up this part twice, but it doesn't matter because you take union. So it is to be write as more clear way, x product minus I product b, it is x minus a product y unite with x product with, okay, yeah, it is not a proof, but it is a sketch of a proof, because we we made an assumption that a is that part. Okay, it doesn't make any difference if you assume the a is have other parts. As like I said, we need this lemma to prove our main idea. So our main theorem is not theorem but claim the boundary of x Cartesian product with y is an x. Okay, to give a slight idea about this, you have x and y like this. and you need to define this boundary, right? This, okay, x has a boundary, these 2 points, and y has a boundary, these 2 points. If you unite x's boundary with y and y's boundary with x's, you get the same boundary, right? You get first boundary of x with y, these 2 parts, and with a boundary of y and Cartesian product with x, you get these 2 parts. So you end up with red boundary of x, Cartesian product y, union x, Cartesian product with boundary of y. Okay, but we are going to prove it concisely. So proof concretely, I'm sorry. Okay, first, what is the definition of the boundary? Boundary of x is like x's closure minus its interior, right? And I define this like this little dot. So our claim is, what is x and y? So we are need to first find closures, then their interiors. Okay, like you say, you can take out this closure. It is given in the Micros book, so it can be written as x closure product with y's closure and minus x's interior, and it is also given in the book. I'm going to write a link below the video. So, and you can use this above lemma. These two, of course, you have closure and interior is the subset of it, right? So we can use this lemma above, and likewise in the y cases. So using lemma, we got a big one minus little one here, and which means x's closure minus x's interior, Cartesian product with y's closure, and minus, not union, x's yani x closure, Cartesian product with y closure minus, and little one is y's interior. Okay, so by definition these are x's boundary and this y's boundary. So write it again. Boundary of x, Cartesian product of y's boundary, closure, union, and x's closure, Cartesian product. Right? So I have said that this should be y and x, but their closure, of course. Okay, and here's the idea. If you have a like okay, I'm writing again a rectangular. Okay, think as there are no points in x, so they are excluded, and there are no points in y. So you cannot say that these are okay, these are the boundaries. This cannot be the space x Cartesian product y's boundary, because you should include these all points at the boundary. So that's why you take closure. You close these gaps with the closure, and you take then a boundary, and then it makes sense. So this is the final formula with the proof. So we needed to use this lemma, but I'm sorry about the not concreteness of the proof, but our main idea is that. So thank you.